Thanks again for joining, all of you. As you can see, I'm not Tom. Tom's unavailable today, so I'm going to moderate today's STROBE-X talk. Thank you all for joining in. I know what is often a vacation week for many people, so excited to see lots of you here. We have an exciting talk today by Pallavi Patil of the NRAO on AGN in the era of multi-epoch radio surveys. So take it away. Excited to hear what you have to tell us.
Thank you, Ed. Thank you everyone for joining in today and just giving me an opportunity to talk at the STROBE-X meeting. I've joined STROBE-X team recently, so I'm just excited to share some of the radio work that I have been doing and that I'm excited about. I'm a Jansky postdoctoral fellow at NRAO New Mexico. Before that, I did my PhD at another NRAO in Charlottesville. And throughout my work, I've been mainly looking at young radio AGN in the continuum domain. And time domain is something that's new for me that I've just started to look at. And today I'll talk a little bit about sort of the upcoming radio surveys and some of the exciting AGN science that we can do with time domain and variability. So let's get started. Here's an outline of my talk. As I told you, this is going to be very AGN heavy, but after my talk, feel free to talk about any other applications of radio surveys and other populations that we can study with this new upcoming radio surveys. So with that, I'll give a little bit of background about AGN and the sort of history of the radio surveys, then talk about some of the radio variable AGN and some of the results that we are seeing, then some of the work that we can do immediately with the new and upcoming next generation telescopes. And in the last few minutes, I'll talk a little bit about the prospect with STROBE-X, and then we can discuss a little bit more about other objects that we can study. So since this is going to be AGN focused, let me just quickly introduce AGN to people who may not be familiar with it. AGN, or active galactic nucleus, stands for galaxies in which the central supermassive black hole is actively accreting, because of which AGN are some of the most energetic and luminous objects in the universe, and they're long-lasting compared to other transients. But today I'll be focusing on a subset of radio AGN, which are called radio loud or radio AGN, in which these collimated jets that you can see here for one such galaxy are emitted from the central black hole. And these are just the streams of relativistic particle, and they can travel very long distance way outside the host galaxy. And some of the reasons that we study radio AGN and jets in general is because jets do have some cosmological impact. They can influence the whole host galaxy evolution. And that's sort of something that's kind of a current hot topic in trying to understand jet ISM feedback across space and time. As you may all familiar with it, AGN is a quite complex system. There are different components emitting in different parts of the electromagnetic spectrum, and because of which, directly or indirectly, we can observe AGN emission at all frequency, at all wavelengths. Today, I'll just focus on the jets aspect of it, the radio emission that's coming out of radio jets. And the other thing that can be interesting for today's talk and the variability in general is that AGN are variable at all bands, at all electromagnetic frequency bands. Here I'm showing a light curve of 3C279, and you can see that starting from gamma ray all the way to radio, there is some variability associated with AGN, making it an interesting object to study in this time domain astronomy and multi-epoch radio survey. So now moving on to talking about radio surveys, I'll just quickly tell you, radio sky is, this is something how a radio sky would look like if you had radio vision. It's completely different than optical sky. Most of the emission that you see here, these are all extragalactic sources. Most of the stars that we see in the optical sky just do not emit that strongly in the radio. Primarily, all the brighter objects that you see here are all radio AGN. So that's something that's different about radio sky in general, that all the objects that we're looking at, the brighter ones are especially extragalactic. And just for the bookkeeping purposes, I'll be talking a lot in the frequency range of frequency values. So when I say radio, I'm talking about frequency ranges between 100 megahertz to a few tens of gigahertz. And in wavelengths, it roughly corresponds to meter to centimeter wavelengths. So that's what I'm defining my radio sky here. And so just going to a little bit of a history of the radio surveys. So radio observations and radio has been around for a while. As you can see in this plot here, starting from 1940s, radio surveys have been conducted for over many, many decades. There have been some expected, unexpected discoveries. AGN obviously were the first one to be discovered in the early 50s, 60s, and then it just, the whole field started booming after that. You can sort of divide the radio sky surveys in sort of 3 different eras, and they are mainly technology driven. 60s and 70s was a time of Cambridge catalogs. These are narrow band, low resolution, very sensitivity limited surveys. But that's where you could see all these beautiful large scale giant radio galaxies that we all are used to seeing. At that point, only hundreds of sources were observed so far. And a lot of the efforts that went in after this was in trying to identify the host identification and trying to understand a little bit about the sources themselves and their accretion physics in details. And this is what I was just talking about. The 60s, 70s, and time, a few years or decades after that was spent on trying to understand these beautiful large-scale FR1, FR2 types of radio galaxies. And it was only these brightest ones that were studied during that time. Then came these interferometers. So they started building up in 1980s and 1990s. Here I'm showing a few examples. And there's a lot in this plot, but the key point is that the interferometers started creating these started observing this entire sky at much higher resolution and much better sensitivity. And this started resulting in these sky surveys that some of you might be familiar with, it, NVSS, TGSS, and all these newer sort of a legacy radio surveys that many of us use. Because of interferometers, sensitivities were down to millijansky levels, covering a large area of the sky, almost all sky. And these tiered designs of radio surveys started happening with all sky, and then starting to focus on these few fields and trying to understand more details of different populations that you can see at fainter levels. The key science topics after that were, trying to conduct systematic surveys of AGN, looking at star-forming galaxies and trying to understand connection between black holes and galaxy evolution. So, but with all that, all you can see, one thing is that all of these surveys were all taken at single epoch or single frequency, which was covered at a very narrow band. So there was never, so radio astronomy or radio sky surveys in general have been lagging behind other wavelengths in terms of, trying to observe the sky over multiple epochs. And this is something that's happening only recently. And that's because of technology driven, as I said. Recently, many of the new interferometers or older interferometers have gone through a huge sensitivity upgrade. And here I'm showing some of the legacy ones that I talked about, such as WENS, SUMS, and VSS. And then there are these new ones that are coming up, such as VLA Sky Survey. The difference you can see between them is that the wide sensitivity or the wide instantaneous frequency coverage, and that sort of gave a huge boost into observing, and you can just do a quick look observing in the radio sky surveys and sort of do it, come back to it every couple of months or years with that. And with this sort of a synoptic design now, we are finally getting into the time domain astronomy in the radio. So yeah, the point is time domain radio sky or radio studies is sort of something that's a relatively recent field, only maybe a decade old or so. At least it has been known that radio sky is dynamic, but it's like conducting sky surveys is something that's doing in a multiple fashion is something that's quite new. So here is the dynamic radio sky. Now the multi-epoch survey designs that are coming up in these newer facilities is allowing you to reveal this wide range of transient, galactic, extragalactic, and as well as variable populations. There are so many objects that are transient or variables that you can study. But today, now I'll be talking about only the sort of the studies that are coming out of AGN in here. But after, feel free to talk about more objects that we can study with the new and the upcoming and the next generation radio sky surveys. So one key survey that I will highlight in my today's talk is VLA Sky Survey. As I mentioned, VLA underwent a huge sensitivity upgrade. VLA is the Very Large Array, is the interferometer in New Mexico. And because of this huge sensitivity upgrade, you can have a very much wider spectral coverage, or you can observe over a wide range of frequency at a time. So compared to the first and NVSS, which were the older VLA or Very Large Array Sky surveys, VLASS or VLAS is sort of has a huge jump in the sensitivity as well as resolution. And also it's taking at a higher frequency. So you do have sort of a spectral information as well. The goal is to observe the entire northern sky, as you can see here, which is highlighted in this, over 3 times or 3 epochs in the span of 7 years. VLA is currently in the epoch 2 of the observing. Epoch 1 and all of its and the quick look imaging that happened, all of the data is available on Sidata if anyone wants to look at it, or just use it for their science. There are plenty of opportunity with observing the entire sky. By just observing over more than 1 epoch, you get a lot more out of it. Some of the opportunities are time domain studies, as I've been talking about. Also, you have a high resolution, but accurate radio images for other multi-wavelength surveys. So there are a lot of opportunities and synergies with the other multi-wavelength surveys as well. Just to give an idea of the improvement in the resolution, here is the NVSS, which was the 1.4 gigahertz, the first VLA Sky survey. And then the first was a high resolution survey, but it cannot observe the entire sky, but only the patch of it. And then this is VLAS, which is sensitivity improvement and resolution improvement can, give you a lot more information about the structures or morphologies of the sources here without losing any of the sensitivity to extended structure. So yeah, it's been really, VLAS it's great, and there's a lot you can do with it. Let me tell you a little bit about the dynamic radio sky. And this was one of the immediate study that came out of just 1 epoch of VLAS observing. This is a work that is mainly done by Dylan Dong. His PhD thesis was to look at sources that were observed in FIRST, which are highlighted in this purple area, and compared with the radio catalog that you can get, or radio sources that you can observe with VLAS. And you can see here that the difference was about a decade, or the time difference was about a decade or 15 to 20 years. First, again, all of the older surveys were only taken at 1 epoch, whereas VLAS has 3. Dylan looked at the first epoch and created a catalog. He's looking at a wide range of sources or transients that you can see between FIRST and VLAS. The work that I'm involved in is the AGN. So there are about 600,000 sources between this overlap of 10,000 square degrees. And interestingly, many, in fact, about a few thousands of sources are detected in VLAS that are not there in FIRST. And some of them do correspond with AGN. And this is the work that was led by Christina Nyland, and that I'll talk a little bit about and that I was involved in. So sort of a question, big picture questions here that we are interested in with the time domain surveys is that what can we know about radio jets with the multi-epoch radio surveys? So here I'm showing a sort of a cosmic history of the universe, starting from Big Bang to present day. Large-scale jets are well established that I was just talking about because we have been studying them for decades. However, compact jets or young jets is something that sort of has been known for a while, but they haven't been studied in a systematic way. So one of the ways we can study them is by using multi-epoch surveys, such as the study that Christian Island and I worked on. So basically, all the multi-epoch surveys can help us give us a census of these compact jets across a much larger volume because of the sensitivity improvements and the depths. There's another question of jet ISM feedback that I was talking about. And in trying to understand some of these surveys, we also need to make a progress on finding new ways to build up samples of young compact jets at lower as well as a high redshift. And this is where a multi-epoch surveys can be really useful in trying to make use of agent variability and trying to identify these young radio agents in a new way. Another thing, the radio variability of AGN can come from different effects. This is something to keep note of. There are a lot of extrinsic effects and intrinsic effects as well. Here I'm sort of summarizing them. And the timescales of the radio variability can be from few hours to months or decades. And there are different reasons for each of those timescales of variability. Extrinsic variability ranges from hours to days, and there are different reasons for it. I'm not an expert on this, but just sort of, we can just give you an example. Here is one paper by Vedantam that you can look at. One of the things that people are interested in trying to understand is the origins of intrinsic variability with the multi-epoch radio surveys. There are a couple of reasons that can give rise to it. Jet reorientation, or sort of a dynamic evolution or expanding source, can also vary over time. And this can be, depending on the cause, it can be months to decades long. And amplitudes can be typically very large here compared to extrinsic effects. And so basically, the current surveys are trying to look into it, but next generation surveys can sort of, will need to consider these effects when they want to decide on the cadences and depths, and because it will be essential to separate out these different effects if we want to have a clean samples of radio variable AGN. So one thing that I'm particularly interested in, and that I'll just talk about, that I've been hinting at, is the dynamic young jets and their evolution. As I mentioned, the brightest of the young radio jets have been studied for many, many decades. These are typically have fluxes of millijansky or Jansky levels. And so literature on this subject is quite extensive. The good point is that we have a good idea of how the properties of these young jets change over time. And we can sort of design the surveys or try to find ways to identify these sources by knowing what sort of expected variabilities for these sources. Here I'm showing a graphical picture of size versus brightness. So typically young jet brighten as they grow older. So with multi-epoch surveys, you can really probe these youngest jet phases where the variability is significant enough over a timescales of few years. The other thing that's interesting is spectral shape. Typically young jets have a peak spectral shape, as you can see here. And this is our sort of an observable band. And this turnover is because of some absorption, intrinsic or extrinsic to the internal or external to the radio plasma or the radio jets. And as they grow old, this location sort of shifts towards lower frequency, and it just goes out of our observable window as they age. So these two sort of key properties can be used in the multi-epoch surveys to study or identify samples of young jets. And this is what the study by Christian Island was looking at. So basically, I mentioned about the dynamic sky between first and VLAS, right? So some of the sources that were not detected in FIRST, but were just, bright and visible in VLAS, were associated with SDSS quasars. So they were known optical quasars, but they were initially radio quiet. That means there was no radio emission, but now you have a millijansky level, a significant radio emission associated with it. She conducted a follow-up VLAS observation over 1 to 18 gigahertz to sort of map out this radio spectra across a wide frequency range. And as we talked about, as I just mentioned, that it is consistent with being a curved shape rather than a straight power law, which you typically see for older lobes. So this follow-up observation have confirmed that these sources that have been sort of become radio loud from radio quiet in VLAS are consistent with being potentially young jets that were heavily absorbed to be detected in FIRST. There have been other studies similar to this. There's a new category of AGN called changing look. Basically, this was a survey that was conducted by Kunal Moody and other people in this collaboration where they looked at Caltech, this is a survey called as Caltech NRO Stripe 82 survey, or CNSS, where they observed a strip of a sky over a couple of years, and they found that some of the quasars brightened and faded dramatically in the radio bands over timescales of years. Here I'm showing one as example. And basically the reason that they think this is that there is the triggering of the radio is sort of a result of quasars accretion property, and accretion state is changing, and which is resulting in this variability in the radio. And that's it's quite interesting that we can do with just imaging in one frequency over time. There's another, so hopefully I've convinced you right now that radio spectra, even at a single epoch, can be quite useful in trying to identify these young compact jets. What you can do a lot more if you have a radio spectra over wide frequencies over multiple times or multiple epochs. And this is a sort of a study that has been in work for the Chris Nyland et al. 2020 sample. Here I'm showing on the left, and on the right is another work that is done by Catherine Ross using peak spectrum or the young jets that they found at GLEAM, which is a sky survey of MWA, which is another radio telescope. So what they're finding is that actually the radio spectra over multiple epoch can be a very powerful tool to diagnose or investigate the origins of radio variability. Because depending on whether spectra change over time or not, you can know a lot more about what's going on in the source. A steady spectra, that means no change, or is just changes at low frequencies, would be consistent with a young evolving jet, because as we looked at, as a source expanded, becomes bigger, and the location of the turnover sort of shifts towards lower frequency, and you see significant change at after the turnover. Then there are some sources where they're entirely changing their spectral shapes. No one knows, this could be beam sources or not, don't know what's going on. And a lot more sources such as these would be needed with a multi-wavelength follow-up to understand what's going on. And then there are some sources, if you observe over intra-day timescales, you can sort of look at the interstellar scintillation or these extrinsic effects that change radio spectra. So so sort of this whole suite of studies that are coming up is creating this need for sort of creating, looking at the cadences to match various timescales. So for example, from Catherine Ross's study here, she's suggesting that at megahertz, hundreds of megahertz frequency, you need cadences of months to years. Whereas if you want to look at the variability in the gigahertz, you need hours to days to sort of separate out origins of variability. And that's sort of something that we would need to look at once the newer generation surveys are going to come up. So one thing that I led during my PhD, and is something that it's not exactly time domain, but it's sort of has a good synergy with it, is constraining spectral shapes by just combining different radio surveys. One thing that's becoming clear is that one survey cannot do it all. You need to, and to identify, study the spectral shapes of, or just have a broad understanding of spectral shapes, you will need to combine different surveys, different radio surveys, to sort of get a complete coverage of the radio frequencies. And this is what I did during my PhD. I did it for a sample of, a specific sample of heavily obscured quasars that also had compact jets. But this is not easy. These surveys span range of observing frequencies with their own systematic biases and different epochs. So this is something that's non-trivial, and this is something we will need to sort of worry about as well when combining different surveys. But this is something that can be a first stroke before trying to do investing a lot into a follow-up observations, which can be time-consuming and costly. So here I'm just showing some few examples. There are so many other surveys and instruments in the time domain for the radio, in the radio wavelengths. Obviously, I cannot cover all of them. I'm just listing a few of the other interesting instruments that could have potential synergies with STROBE-X as well. Well, not on the timescales, but also on the aspect of designing. There's a survey coming up on SCAP, which is a precursor of SKA, or square kilometer array, where they're conducting a vast or a variable and slow transient survey. They're observing a 10,000 square degree sky. They're planning to observe it daily for over 2 years, and this will be a shallow, quick look imaging. And the same sky, they're going to observe with a deep observations, and they will provide 7 epochs over a time scale of 5 years. This will be sort of a next step to what VLAS is doing, getting something on a shorter cadence, and as well as something on a high cadence, and something on a more of a longer cadence, but with the deeper and probing fainter populations. There are also commensal surveys that are going on right now, just to understand known and unknown population. VLight is a commensal instrument that is put on the VLA. There is a Thundercat on Meerkat, where they have a trigger pipeline, and if you detect a transient, then it goes through a Thundercat pipeline and trigger a follow-up observations as well. So yeah, overall, there are so many instruments that are going that will be looking at the time domain aspect, or conducting multi-epoch surveys in the radio over the next few years. And what lies in the future? Some of the upcoming facilities that would have some possible connection with STROBE-X. Here I'm listing a few: DSA 2000, NGVLA, and SKA mid. So DSA 2000 is a deep synoptic array, which is a true synoptic telescope. It will have 2,000 antennas in the Owens Valley with a wide spectral coverage. The prime phase of the survey is between 2026 and 2031. It's not a perfect match with STROBE-X. NGVL is something that would be a good follow-up instrument. This is a replacement to the current very large array. It does have a very high survey speed, so it can be a good survey telescope as well. Another good telescope that would be within the timescale when the STROBE-X would go online is SKA, either 1 or 2, depending on how their construction goes. SKA1 is planned to start in the next, the full operation for SKA1 will plan to start in the next few years. And they do have plans to have subarrays when they're not the arrays that are on the outer on the outer boundaries of the telescope design, which are not being used, will be used to do this time domain sort of sky surveys and searches. So that would be something interesting to consider with STROBE-X. or any other multi-wavelength surveys. Future prospects. So overall, there are so many things that you can do with this next generation telescopes. Here I'm listing the AGN science that we can do, but the one that sort of is interesting or relevant to this talk is the multi-epoch survey design. With this sort of a survey design, you can identify more and more samples of compact young jets, and also elusive radio AGN, which are elusive as an obscure radio AGN, which are not easy to be detected at other multi-wavelength surveys, such as optical, because they're too faint to be detected. So just give you a little bit details of what can be done with this next generation telescope. The DSA 2000 will have this condensed all-sky survey, which will observe the entire sky for 16 times or 16 epochs over every 4 months. So this is a very high cadence survey with unprecedented survey speed and much sensitive or much smaller flux levels or flux limits than before. So DSA 2000 is expected to identify more than 100 million AGN, but the prime phase is between 2026 and 2031. So I'll talk a little bit about the timeline as well here, but this is the current plan. But it can be something like we study before and then sort of go do a follow-up with other X-ray surveys. So that can be done with this. But if timeline matches, this could be a perfect survey to have comparison with STROBE-X observations. Next generation or very large array or NGVLA, it would provide a wide range between 1 to 100 gigahertz. This is a telescope which will replace the current VLA with about 200 telescopes or 200 dishes and 30 dishes on longer continental baselines. It can be a good follow-up instrument, as I was just saying. The sources that will be detected in the synoptic surveys can be studied in more details with the NGVLA. NGVLA can routinely observe in a parsec scale images of compact jets with much better sensitivity. You can also robustly characterize the turnover and try to understand the causes of absorption at low frequencies. That's something that can be done on not just few sources that we are doing right now with current surveys, but many sources, statistical samples of AGN. So to summarize, many exciting opportunities are ahead with the radio surveys, and the dynamic radio sky or dynamic radio studies are sort of set for a revolution with all these current upcoming facilities, and as well as the new instruments that are being built. Here is a sort of a quick summary of survey speed versus continuum sensitivity. And the 3 key instruments that I just talked about, DSA, NGVL, and SK, would be really great in trying to understand radio variable AGN. Some of the key topics that will be focused on would be origins of understanding the intrinsic variability or radio variability of AGN, and trying to delineate between different effects. Also trying to get a complete census of occurrence of variability and all of the other statistical samples of different AGN would be a topic that would be focused on, can be focused on in the next few years or so. So in the last few minutes, just sort of, I'll discuss a little bit about the prospect with STROBE-X. Just to give you a quick, honest opinion, I'm coming in from radio. I'm very new to X-ray observations of AGN. So please help me figure this out as well. I'll try to talk a little bit about my understanding of it, but yeah, feel free to jump in and let me know what sort of synergies that we can expect between STROBE-X and radio sky surveys. One thing that I thought would be a good instrument to be used would be the wide field monitor, which will be observing the entire sky over a couple of epochs during its time of a few years or 5 years, I think. But along with that, just its spectroscopic capabilities would be a good plus to get light curves as well as give a good high sensitive spectral X-ray modeling for these new populations or the new samples that we will discover with sky surveys. One concern or one of the topics that I was just thinking about is the timeline. All of the surveys that I talked about, for example, DSA 2000 will be over by the time STROBE-X becomes online. One of the good instruments that would be operational to get a sort of a quasi-simultaneous monitoring of different populations would be SKA. And NGVLA is set to start its science operation in mid-2030s. So there might be some partial overlap with it. But if not a quasi-simultaneous monitoring, but a sort of a asynchronous comparison of dynamic radio sky and X-ray sky could be something that can definitely be done with STROBE-X and different radio surveys that we have. And as I talked about, possible use cases for wide field monitor. So the key population studies that we will look at with multi-epoch radio surveys is newborn and younger compact jets, obscured AGN, and low mass or radio quiet AGN. So maybe wide field monitor could provide light curves for maybe at least the brighter sources in these different categories, or just maybe by stacking different observations, you can study maybe a subclasses of AGN over a months to years of time scale. So sort of a basically monitoring of different AGN populations that in the X-ray, and sort of trying to understand the connection of variability with different AGN properties. That could be one potential aspect that STROBE-X can help. The other thing that, since I've been looking at obscured AGN for my PhD work, I sort of started thinking about a little bit more about understanding X-ray modeling of obscured AGN. So they have been difficult to observe in soft X-ray, obscured AGN, and hard X-rays, and hence the coverage of wide field monitor, which goes from 3 to about 50 kV, can be an interesting way to sort of try to find more and more samples of obscure AGN, if not to a larger distance, but at least a relatively local universe, and constrain their torus properties and obscuring column to much unprecedented sensitivity can be a way to sort of study these different, would be a way to go for this obscure AGN population. So with that, I'll sort of end my talk with the summary. So just to summary, the times domain study are set for a revolution with upcoming multi-wideband multi-epoch radio surveys. Key topics that I talked about were spectropolarimetric studies of young and compact jets, also probing origins of AGN variability and taking census of faint radio population. STROBE-X wide field monitor can help us provide light curves for at least some of this radio variable AGN. But this one thing is that we will have so many other multi-wavelength sky surveys along with radio. So just using all of them to try to sort of understand, get a holistic picture of these different populations can be a good way to go about this. Timeline overlaps can be something that can be a challenge in designing any survey. And also in radio survey, one thing that I didn't talk about is challenges in analysis and calibration of data and trying to come up with unique algorithms to sort of do this in a more accurate way is going to be quite challenging. With the current data rates and with the next generation, the data rates are going to just increase exponentially. So that's going to be a challenge in creating these sky survey within a reasonable time. So with that, I'll end my talk and thank you for listening, and I'm happy to take any questions.